Good morning, everyone. Thank you for coming to listen to this talk. Okay, so my talk is about on the minimum volume entropy of finitely generated group. Okay, let's start with an introduction. Let Z be locally finite simplicial complex, and G be finitely presented group acting freely and co-compactly on Z. We endow Z with a locally finite measure mu and the length metric rho. Both of them are G invariant. Okay, now we fix Z0 on Z in Z and let B Z0 R the ball centered in Z0 and of radius R. And the equation 1, ENT Z mu rho given by this limit. Okay, the limit here exists because of submultiplicativity of mu according to R, and it doesn't depend on the choice of point Z0. So we will see two cases. The first one, if Z is a Cayley graph, where S is a finite and symmetrical system of generators. So here mu is the same of the sum of direct measures given by this, centered in G or in G. And rho is the combinatorial distance on Z. Here we consider rho like the distance, the length of each edge in Z is equal to 1. Okay, in this case, the measure of the ball is called the growth function. Let's see some recall. When we speak about growth function of the group G, means that group G may be of polynomial growth, exponential growth, sub-exponential growth, and intermediate growth. We will see some of this growth. Okay, the equation 1 in this case becomes or represents the algebraic entropy of G relative to S, and we write the equation 1 becomes ENT alg of GS. Okay, first remark, G is said to be of polynomial growth if there exists an integer m, a, b positive reals, such that the growth function mu is given or bounded by this polynomial on R, is of exponential growth if we have this condition, and it is of sub-exponential growth if we have this condition. Okay. The remark 2, okay, the growth of function G doesn't depend on S, means we can change the system of generators without changing the growth of G. Some examples. Okay, so the abelian groups are of exponential growth, and the free abelian groups are of polynomial growth. The Bond-Slack solitaire groups given by 2 generators and 1 relator. When the parameters mn is equal to 1, 1, we obtain this group, free abelian groups, which is of polynomial growth. If mn equals to 1, n, where n is different to 1, is of exponential growth. When mn is equal to 1 or equal to 1 minus 1, we speak here about a fundamental group of bottle clean, and it is of sub-exponential growth. Now, we define the minimal algebraic entropy of G by taking the infinimum on S of algebraic entropy relative to S. So S range over the set of finite system of generators of G. Yeah, remark, okay. If the minimal algebraic entropy of G is strictly positive, then G is of uniformly exponential growth. The second case, let X be a finite M simplicial complex, and its fundamental group is equal to G. We endow X with a Riemannian metric H, and we take here Z by the universal cover of X, and H hat the lifting metric of H on X hat or Z, and rho is the distance induced by the lifting metric H hat. Here, the measure mu is the M measure of Hausdorff corresponding to the distance rho. And we write the volume of XH given by this sum. Yeah, okay. So the equation 1 defines here the volume entropy of X related to H. And we write this. Okay, now we put omega of XH given by this product. We write this so that omega of XH is not influenced by the homotheties. I mean that here, if we take H or lambda H, it will not be influenced by homotheties, this quantity of omega XH. And we define the minimal volume entropy of X by omega X is given by an infimum on H of omega XH, where H here range over the set of Riemann metric on X, sorry. Okay. We will see that the minimal volume entropy of X does not depend only on their fundamental group. It also depends on their topology. Like, yeah. Okay, so for that, let Y be an M simplicial complex. There exists a linear application. F goes from Y to a classifying space of P1 of Y. And so by realizing this classifying space as a CW complex, we can choose F like a cellular application, which sends a simplex of Y to a simplex of M skeleton of classifying space. Okay. Definition. Y is said to be non-essential if F is deformable onto an application Ft from Y to M minus N skeleton of classifying space. Otherwise, Y is said to be essential. Remark. Any two simplicial complex of non-free fundamental group is essential. Because why? Because we cannot have application F theta goes from two simplicial complex to one simplicial complex, and which have the same fundamental group. So any two simplicial complex of non-free fundamental group is essential. Okay. For X, non-essential simplicial complex of dimension M, we have omega of X, its minimal volume entropy, is equal to 0. Here, the idea of proof, we can find a simplicial complex of dimension strictly less than M, and which has the same fundamental group than X. So here, when we calculate omega of Kx, it will be less or equal to omega of Y, if we take Y is this complex. And when we calculate its minimal volume entropy, we will see that Y, it doesn't have the M simplex. So the M volume of this simplex is equal to 0, because we don't have the M simplex for calculating measure. I hope that you understand what I'm saying. Okay. Now, the minimal volume entropy of groups. Here, we need to use the minimal volume entropy of complex. G being non-free finitely represented group. on defines the minimal volume entropy of G as the following, in the equation 2. Okay, yeah. Okay, how can I say it? G here has to be a non-free, but in the case if G is a free group, Fn of rank n, we consider here in equation 2 unidimensional complex. Why? If we apply this definition for this equation 2 for free groups, we get 0. Omega of Fn here will be equal to 0. Why? Because the complex here are non-essential. So omega of y in this case will be equal to 0. But we have we know the omega of the omega of the minimal volume entropy of graphs is given by this formula. So we can we deduce the minimal volume entropy of free group by this. By the minimal volume entropy of graphs. So omega of Fn is given by omega of gamma n, where gamma n is of fundamental group Fn, is given by this formula. Okay. First proposition: if G let G be a non-free finitely presented group, and H is a subgroup of finite index K, omega of H is given by is bounded by this square K omega of G. Here, the idea of proof here, we take a quasi-optimal complex of G, and we will see X. We can call it X, and we take its cover of K-shaped. Yeah. Okay. Second proposition: for G1 and G2, two finitely presented groups, such that at least one of them is non-free, then omega 2 of free product is bounded by this sum. To prove this proposition, we need this theorem by supposing that K1 and K2 are quasi-optimal complexes of G1 and G2 respectively. Yeah. Okay. So if both of them are free, here we will get something wrong. We can say it after this example. Okay, so let's see. We have a group G, PSL 2Z, now given by this free product. It satisfies omega 2 of this group is given by this bounded by this sum. Both of these groups are of sub-exponential growth. So omega of Z2 equal to 0 and omega of Z3 equal to 0. So the sum equal to 0. Okay. The remark for G1 and G2 are both free. We can replace here omega Fn free product with omega Fm. We calculate omega Fm plus n. We get something that more than omega Fn plus omega Fm. It's why this condition, at least one of them is non-free. Yeah. Okay. Now let's see another concepts of minimal volume entropy of groups given by Brigman and Clay. Before this, let's see this definition: a geometric definition of group. Geometric dimension, sorry, of group. G be a group, the geometric dimension of G, not GD of G, is equal to the smallest dimension of all its classifying spaces. The fundamental groups of aspherical manifold are of finite geometric dimension. The same thing for Bond-like solitary groups are also of finite geometric dimension. Also for right-angled earthing groups. Okay, the definition of minimal volume entropy given by Bridgman and Clay. G be group of GD finite geometric dimension. Omega prime of G is given by this n phenomenon, omega x on x. X ranges over the set of all M aspherical simplicial complexes such that P1 of X equal to G. So you can see here the difference between this definition and the definition given before. So here we see the all M aspherical simplicial complex, but the definition before we see all two simplicial complexes of fundamental group G. Okay, so we can ask this question, like which conditions on G such that omega G is equal to omega prime of G. Now, in general, we have omega G is bounded by omega prime of G when the geometric dimension is equal to 2. Why? Because here the set of all two aspherical simplicial complexes of fundamental group G included in the set of is included in the set of all two simplicial complexes of fundamental group G. Is why we have certainly this inequality. Okay, so when G is equal to G is a free group, omega Fn is the same that omega prime of Nn, Fn. And when GD is bigger than or equal to 3, they are different. Okay, now here we will see example showing us the difference between omega and omega G and omega prime of G when the geometric dimension of G is bigger than or equal to 3. Here we'll see for dimension 3. SG being orientable surface of genus G bigger than or equal to, and T3 the 3 torus. So here the complex K given by the weights of SG and T3, the dimension here is equal to 3. We denote by G its fundamental group given by the free product. Okay, so K is 3 of dimension 3 and aspherical complex. Okay, recall the theorem of Babenko and Saburo that we use here just. Okay, we can write omega, the minimal volume entropy of K, omega 3 of K is given by the same omega 3 of SG plus omega 3 of T3 by using this theorem. Okay, and okay, so the dimension here of SG is equal to 2. So omega 3 of S2 is equal to 0. Why? Because we don't have a 3 simplex. SG doesn't have 3 simplex. Look, its 3 volume is equal to 0. And okay, alors, for this instance, forget these sentences. We have to start now. Omega 3 of T3 is equal to 0. Why? Because its fundamental group is of polynomial growth. Then we get omega 3 of K equal to 0. I mean, this is 0 plus 0. It gives us omega 3 of K is equal to 0. And then omega prime of the group is also equal to 0. But this proposition shows us that omega G of this group is strictly positive. There exists a positive constant A such that for each G is upper than or equal to, and for any finitely represented group H, this group G satisfies this inequality. So we can apply this proposition on our example, and it gives us this inequality. So like here, you can see the difference. Omega prime is equal to 0, but omega is strictly positive. Yeah. Some results. Let G be a finitely generated group of geometric dimension equals to M, and sorry, like this. So we have this. Omega M of H is bounded by the M square of K, omega M of G. For position 5, G1 and G2 be two geometrically finite groups. The geometric dimension of G1 equals to geometric dimension of G2, strictly bigger than 1. So we have this inequality. If the geometric dimension of G1 is strictly less, strictly less than geometric dimension of G2, we have this. Why? If GD of G1 strictly less than GD of G2, here we get omega M of G1 is equal to 0, and here something different to 0. So omega M of G1 free product with G2 is bounded by omega M of G2. Yeah. Okay. The third part of this topic. The volume entropy of some graph products. What is a graph of groups? Gamma B connected and oriented graph, which has V vertices and E edges. We take G, the family of groups. We have V groups. We call graph of groups of gamma G, the graph gamma, such that on each vertex of gamma, we place a group GE, and along each edge, we put an homomorphism, PIG, from GE to JG, or PIG from JG to GI. It depends of the curves. Yeah. Okay. Now, the cell complex K gamma G, from gamma G, the graph of groups, we construct a cellular complex K gamma G by associating to each group's GE its classifying space. We take one classifying space, and for any homomorphism PIG, we associate it with a cellular application, PIG, from this classifying space to classifying space of JE. Okay, so to conclude this construction, we associate a cylinder to each row. Okay, here, like just a remark, we can we take a monomorphism and not homomorphism, and we do this for getting the for this. Okay, coming definition. we call the fundamental group of this complex the graph product. So the graph product is the fundamental group of this complex. Okay, so I spoke here about monomorphism and not homomorphism, is to have something, sorry, it's for P1 of K gamma G, it will given by the free product, not free product, sorry, the direct product of these groups GI. If we take a Laplace, if we take monomorphism and not homomorphism, we'll get P1 of K gamma G like the direct product of GI. Example, if all groups GI are isomorphic to Z, then the corresponding graph product is called generally the Bohm-like solitary group, noted GDS groups. They are of geometric dimensions equal to 2, and they satisfy its minimal volume entropy is equal to 0. Okay. Definition. When all E of the family, if for each E, GE is of polynomial growth, the corresponding graph product is called soft growth. For example, Bohm-like solitary groups form a family of soft groups. SL2Z and PSL2Z are also soft groups. Even GD, their geometrically dimension is R infinity. And theorem. Each soft group G satisfies omega G is equal to 0. Okay, so here, whenever the geometric dimension of the G, we have omega of G is equal to 0. Okay, I have this bibliography. So you can see I use this fourth, especially this fourth reference. Yeah, okay. Yeah, I think that it's what I have to do. Thank you for your attention. And sorry for this. I think that I stop here. Yeah.
Okay. Thank you, Thiziri, for your talk. So now it's time for some questions.
Okay.
Maybe I have a question.
Yeah.
Okay. Or did someone else ask? No, because I don't
You can ask.
Okay. Yeah, my question is is someone else talking, because we don't hear anything. No. Okay.
Okay.
So this graph of groups, it looks like you can express it as a functor from like a small category, a finite category, to the category of groups.
Sorry, you speak about which one? Okay.
Towards the end, or how did you call it? Graph group.
Graph product.
Yeah. To define the graph product, you had before you had this.
I'm coming. Okay.
Yeah, graph of groups. This one.
Graph of groups, the first one. Okay.
Yeah. Do you know if there's some kind of category theoretic formulation of this?
Category.
Okay, but then I guess maybe it's not that common.
What do you mean? I mean,
Like if this can be, it looks a bit like a functor from a finite category to the category of groups, and then I mean, yeah. So my question was just if this.
no.
Okay, good. Thanks.
I'm not sure that I have the answer for your question.
Yeah.
I have one question about the proposition 3.
3?
Yeah. Yeah.
3.
I think it's.
Oh, yeah.
Yeah, here I didn't really understand from the relationship with the H and the
Sorry.
the relation. I didn't understand if there exists a clear relationship between A in the proposition and H or G or I mean one of the G's.
For the example, this proposition with our example.
I mean the positive constant.
Yeah. The positive constant depend on G.
Okay, the big, okay.
And we take here G is upper than or equal to 2, because if we take G is equal to 1, we'll get the free abelian group, which is of polynomial growth. So its minimal volume or entropy is equal to 0. It is why we take here G is upper than or equal to 2.
Okay.
J'ai répondu à ta question.
Yeah. Yes. If I have another question. If the complex X is essential in order to have omega X bigger than 0 structure.
Not necessarily, no. I mean, we can have. Okay, so yeah. C'est la proposition. Here. We can have X is X is essential simplicial complex, but this does not give us necessarily omega of X is strictly upper than or equal to 0. We can take, like, for example, we can take X is the torus, the two torus. Its fundamental group is a polynomial group, so it's omega X, omega T2 here is equal to 0. Even it is an essential simplicial complex and not non-essential simplicial complex.
I guess I wanted to ask, so at some point there was an equation of two entropies. I was wondering, because I think I missed like one of the definitions, if you can show that to us again and repeat why, like
this one?
What's the two different things detect, or maybe like what's the interpretation of them? I don't know if you can just repeat that.
Which one? Sorry, you speak about which equation?
So there was, this one, and then an algebraic entropy, right?
Yeah, okay. So we have this equation. The first case, if Z is a Cayley graph of G, so here we get the algebraic entropy relative to S. And here we, by using this, we can define the minimal algebraic entropy of G. And in the second case, if Z here is the fundamental group cover of the universal cover of X, here we speak about the volume entropy of X related to H. This is the difference between the two cases. The first one gives us the algebraic entropy relative to S, and here the volume entropy of X related to H.
Okay, and the algebraic entropy, how was it defined? I think I missed that.
Okay, exactly with the same thing, like equation 1.
Oh, okay.
This is equation 1. So we take the ball in your Cayley graph. We take this ball,
yeah,
and we calculate the measure. And after that, we see the limit. This limit.
Okay, yeah, makes sense now.
Okay.
Thank you.